All right, so this is a recording for 14.2, Applications in Business and Economics. So we're going to talk a little bit about probability density functions. So if you have a probability density function and you wanted to check and make sure that it worked out as a probability density function, you would need to make sure that every point of x has the property of f of x being greater than or equal to 0. The second property is that the integral from negative infinity to infinity of f of x dx is equal to 1. So we say that the function is normalized. If your function isn't normalized, you can still make it into a normalized function by dividing by whatever the integral from negative infinity to infinity of your f of x dx is. So say it came out to being equal to pi, then you could just divide f of x by pi, get a new function with that scalar multiple. And that would then have the property of being, or having its integral over its entire domain being equal to 1. So that's a neat little trick that you can kind of use to normalize functions and create these probability density functions from other functions you might be using. And then number 3, the third condition is that the probability of having a particular entry in a range would be the integral of that range or integral of that interval over the domain of f to be from c to d in this case of f of x dx. And so if you were going from c to d, so some probability of having an instance c being less than your test case, which is then also less than some value d, then that integral c to d of f of x dx is the probability of that actually occurring. And so it'd be some value between 0 and 1 off of that integral, and it would give you the result as to what the probability of it occurring would be. Some examples of probability density functions are the normal distribution, which is this f of x equals 1 over sigma square root of 2 pi all times e to the exponent of negative quantity x minus mu and quantity squared over 2 sigma squared, which is a mouthful and a very complicated function if you're looking at it just from terms of trying to read it and write it and work with it. But it does represent a very neat function, which is useful and normalized and can be reproduced quite easily in terms of just arbitrary statistics that get applied to everyday uses. So you have this mu that represents your mean, which is baked into the function. And it's the very center of where this normal distribution would be located. And then you have this sigma, which is in that function and represents the variance roughly of what the variable or what the particular points would be on this distribution. And so a good way to kind of think about it is roughly how far apart the different points are, the different components are that are in this probability distribution. And so that's the normal distribution. And then we also have a tail distribution. Let's see, I don't know the official term for it. Let me look that up real quick. Well, I know that there's a term for a fat tail or a long tail. So probably something along those lines would probably be what the statistician would call this type of distribution. The most often statistical distribution that you'll hear of is the normal distribution, but there's obviously others that exist. So this one, which would be closer to that example of the telephone call duration, is another option for probability distribution. So we can also talk about total income from a continuous income stream. So if you have an income stream, some f of t, that represents income over time, then you're able to calculate your total income, that r of x or r of t value, if you will, by doing an integral over this f of t with respect to dt. And so if you take a particular range that you wanted to calculate your total income or your total revenue for, you'd be able to pick an A for your starting point and a B for your ending point, and integrate over that range in order to get your total income or your R of T for that particular interval. So that's continuous income. We can also look at another instance of income, which is called future value of a continuous income stream. This is basically where you're investing a continuous income stream into another derivative financial aspect of some investment, where you're able to basically compound the money that you're earning by utilizing compound continuous interest of the certain rate R. And so how this kind of looks is you would take your continuous income stream, you would multiply it by e to the r capital T minus little t. And what that represents basically is the amount of time that you have your particular investment in the actual invested and fiduciary derivative or whatever it is. And so that big T minus little t, that's the time that it's in it. That's the time that it's in that investment portfolio or investment security or whatever it's in after that instantaneous point has been invested at T, little t. The big T is the total time that you're kind of calculating this all over. And so it's trying to figure that endpoint out. And so that's why that big T minus the instantaneous point is that difference that you're integrating, or is that difference that the exponent includes as that time for those particular points. So that means that if you start from 0 and you integrate all the way up to T, you'll be integrating these large exponentials for these first few instantaneous income points that you'll be looking at. And then later on, those income points won't be exponentiated quite as much because the little t will start to approach the big T, causing the amount in the exponential to be smaller, causing the overall value to be closer to what f of t is rather than the exponential value multiplied by f of t. So that's where this f of v equals the integral of 0 to capital T of f of t e to the r of quantity big T minus little t and quantity dt comes from. And it can be rewritten a little bit in order to pull the er to the big, or e to the r big T out, since that's not dependent on what your little t is as a variable. The big T is a constant determined by the total duration that the future value is being calculated for. And the R is a constant because it's the rate the interest is for the particular annuity or investment. So the end calculation, or the nicest kind of way to write this particular integral, comes out to be e to the r capital T times the integral from 0 to capital T of f of little t e to the integral, or e to the exponent of negative RT times dt. And so that's another mouthful, but it is a calculation which is very useful for being able to take a continuous income stream and put it into an investment portfolio and see what the result would be from that calculation. So if you're interested in that, that's what this kind of equation does for you. Now let's talk about consumer surplus and producer surplus. So consumer surplus is basically the concept of how much more a consumer would be willing to pay if you were changing the price to match what they're interested in paying for. So if you take the integral from a particular point that you've chosen, some x bar, p bar for this case, and you integrate over the price demand equation minus your p bar from 0 to x bar with respect to dx, then that would give you this area, and you can kind of see it up here on the graph of where your customers are willing to pay more, but you're only charging them at the p bar price. This is something where if you were able to negotiate with each individual consumer and you're able to upsell them, then you'd be able to sell that particular price point to each of them. But given a particular price point that you wanted to sell to all of the customers, this is what you're going to end up having, and that's going to be the difference that you're going to be left with for that consumer surplus. If you were on the other end of it and you were looking at producers who were giving you supply to be able to sell, then there's a similar equation called the price supply equation, which represents how much a producer is willing to supply to you at a particular price point that you're willing to pay for. And so you can see as the price goes up that you're willing to pay, the amount of supply that is able to be produced for you will also go up. And so in this, you can see that there's a orange shaded region, which is the producer surplus. This is represented by the integral from 0 to x bar of your p bar minus the price supply equation integrated with respect to dx. And so this particular value, this producer supply or producer surplus, will give you what the producers are willing to negotiate down to if you're able to negotiate with each of them individually. And so this is something where you're able to calculate how much more you could save if you were able to work with each individual supplier individually. But this, if you're just paying in general for all of these suppliers at an equal rate, then you would just have your P bar situation. So this gives you kind of an idea of what's kind of there in terms of negotiation potential and how to calculate some of that given some of the mathematics that you have available to you. So those are those topics. Let's talk a little bit about equilibrium price. Now, if you're paying everyone equally and you're charging everyone equally, there's an equilibrium price that you're able to determine, which is this X bar, P bar, where your CS and your PS would end up being equal to each other. The way that you can find that is by setting the demand supply or price demand equation equal to the supply demand or supply price equation. And so if you take those two, you set them equal to each other, then you'll be able to solve for what the X values would make them equal. And that would give you the equilibrium point. And so you should be able to find a point where your price or your demand and your supply are going to even out, and you would have a maximum throughput of your supply and your demand at that point. So that's a little bit more diving into economics and financials and stuff, but it's a very interesting topic, and it has a lot to do with the topics that we've been learning involving calculus. So. All right, that's the end of 14.2.